On the 1st of September 1859, the sky over Cuba turned blood red. In Colorado, gold miners woke up and started making breakfast, convinced it was dawn. It was 1 in the morning. And in telegraph offices across 2 continents, machines that had been disconnected from every power source were still sending messages. The man who worked out why was a 32-year-old brewer's son named Richard Carrington. Carrington was not a professional astronomer. He was a wealthy amateur with a private observatory in Surrey and an obsession with sunspots. Every clear morning, he projected an image of the sun onto a screen and traced the spots by hand, building a record of how they moved. On the morning of September the 1st, he was doing exactly that, when something happened that no human being had ever seen before. 2 points of brilliant white light appeared inside the sunspot group he was drawing. They were so bright he assumed his lens had failed, or that a beam of sunlight had leaked into the room. He ran to fetch a witness. By the time he got back, 60 seconds later, they had already faded. The whole event lasted about 5 minutes. Carrington had just become the first person in history to observe a solar flare. He wrote it up carefully and noted the time, with no way of knowing that what he had watched leave the sun was already on its way to Earth. It arrived 17 hours later. What hit the planet was not light. It was matter, roughly 1 billion tons of electrically charged gas, torn off the sun's outer atmosphere and flung outward at over 2,000 kilometers per second. We call it a coronal mass ejection. When it struck Earth's magnetic field, it compressed it, deformed it, and set the whole thing ringing like a struck bell. The visible result was the largest aurora display in recorded history. The invisible result was that every long conductor on the surface of the planet began generating electricity. People had no framework for it. Auroras are a polar phenomenon. In a normal year, you need to be in Norway or Alaska. That night, they were reported from Cuba, Hawaii, Colombia, and Queensland. Ships in the Caribbean logged crews assembling on deck, convinced a city beyond the horizon was burning. A Boston newspaper reported the light was bright enough to read by and printed a note written outdoors at 1 in the morning using no other illumination. Across the northern United States, people simply got up and started their chores because the sky told them it was morning. The strangest reports came from the telegraph network. In 1859, the telegraph was the only electrical infrastructure on Earth. Tens of thousands of kilometers of bare wire strung between poles. That wire did exactly what any wire in a changing magnetic field does. It generated current. Operators reported sparks jumping from the equipment to their hands. Paper caught fire in several offices. Some machines ran backwards. And in Portland, Maine, 2 operators discovered something genuinely uncanny. After disconnecting their batteries entirely, they found they could still send messages to Boston, powered by nothing but the current the storm was inducing in the line. They worked that way for 2 hours. If you like the kind of science story where the universe quietly reminds you how thin the margin is, subscribe. This channel does one every week. Okay, here's the part that should worry you. The sun's surface is a fluid of charged particles, and it does not rotate as a solid body. The equator turns faster than the poles. That difference winds the sun's magnetic field lines around it like elastic over and over until they snap and reconnect. When they do, they release energy on a scale that is difficult to hold in your head. The 1859 flare released roughly 10 billion times the energy of the bomb dropped on Hiroshima. Almost all of it went in other directions. What reached us was a fraction of 1%. A fraction of 1% was enough to set telegraph paper on fire. One detail makes 1859 exceptional. A coronal mass ejection normally takes 3 to 4 days to cross the 93 million miles to Earth. This one took 17 hours and 40 minutes. The reason is that it was not the first. A smaller ejection had swept the path a few days earlier, clearing solar wind out of the way, so the big one traveled through something closer to a vacuum. It arrived at nearly triple the usual speed, and it hit a magnetic field that had already been disturbed and had not yet recovered. It was, in effect, a 1-2 punch. So what happens if the same storm arrives tomorrow? The auroras would be spectacular. The problem is everything else. The modern grid is a continent-spanning network of conductors, and the vulnerable component is the high-voltage transformer. These are not consumer parts. They are custom-built, weigh hundreds of tons, cost millions, and have lead times measured in months to years. A geomagnetically induced current can push direct current into a system designed for alternating current, saturate the core, and cook the transformer from the inside. Lose enough at once, and you are not waiting for a repair crew. You are waiting for a factory. Transformers are only the headline. Roughly 10,000 satellites are now in orbit, and a strong storm heats and expands the upper atmosphere, increasing drag on everything in low orbit. In February 2022, a comparatively minor storm destroyed 38 Starlink satellites that had just been launched. They simply could not climb out of the thickened air. GPS timing, which underpins financial trading, mobile networks, and shipping, degrades. Long-haul flights over the poles lose radio and get rerouted. This is not hypothetical. In March 1989, a storm perhaps a third the strength of Carrington hit Quebec. The provincial grid collapsed in 90 seconds, and 6 million people lost power for 9 hours in a Canadian march. That was a third. Then on the 23rd of July 2012, a coronal mass ejection comparable to 1,859 erupted from the Sun and crossed Earth's orbital path at full force. It missed. Earth had been at that exact point in its orbit 9 days earlier. Nobody was warned, nobody evacuated, and almost nobody noticed, because there was nothing in the way except a NASA observatory that happened to be there to record it. We are better prepared than 1,859, though the margin is thinner than you would like. A satellite called DSCOVR sits about 1 million miles sunward of Earth, watching the solar wind arrive. Because the particles have to cross that last stretch, it buys us a warning. Somewhere between 15 and 60 minutes. That is not enough time to fix anything. But it is enough time for grid operators to disconnect vulnerable transformers, shed load, and come out the other side with equipment that still exists. Richard Carrington spent 5 minutes at a telescope in Surrey watching 2 specks of light brighten inside a sunspot. He had no idea he was watching 1 billion tons of the sun leave home in our direction. He simply wrote down what he saw and noted the time. That timestamp is the reason we can measure how fast it traveled, how hard it hit, and how much warning we would get if it happened again. The whole of modern space weather forecasting rests, in part, on one amateur being careful about the clock. For more stories where the universe quietly shows its hand, subscribe and tell me what you want covered next.